All right, today we are diving into one of the slickest, most efficient algorithms out there, binary search. Seriously, it's this incredibly simple idea that has a huge impact, and we're going to break down exactly how it pulls off its magic. So, let's start with a little thought experiment. Imagine you've got a massive, old-school dictionary in front of you, and you need to find one specific word. How would you do it with the fewest possible page turns? You're not going to start at A and just flip page by page, right? No way. Your gut instinct tells you to crack it open somewhere in the middle, see what letter you're on, and then decide, do I go forwards or backwards? Well, that very instinct, that's the heart of binary search. Okay, so when it comes to searching a list for something, you've basically got two main ways to go about it. First, you've got what's called linear search. Think of it like a tortoise, slow, steady, and it checks every single thing one by one. Then, you've got binary search. This is the rocket ship. It's brilliant and incredibly fast. But, and this is a big but, there's one catch. Your list must be sorted first. As you're about to see, that trade-off is almost always worth it. So let's start with the obvious, slow approach, linear search, also known as the brute force method. You kind of have to see this one first to really get why the other way is so genius. The logic here is, well, it's about as simple as it gets. You just start at the very first thing in the list. You check it, and if that's not what you want, you move to the next one, and the next one, and the next. You just keep going until you hopefully find your target. It works, for sure, but it's not exactly what you'd call clever. So, in computer science terms, this has what we call O of n time complexity. All that really means is that the search time grows directly with the size of your list, n. You double the list, you pretty much double the search time. Now, for a short list, who cares, right? But what if you have a list with millions or even billions of items? Then this method becomes, well, just painfully, unusably slow. All right, now for the fun part, the divide and conquer trick. This is binary search, and it's all about working smarter, not harder. It takes that dictionary idea we just talked about and turns it into a powerhouse algorithm. But remember that one golden rule, the list has to be sorted. Okay, so instead of just starting at the beginning, we're going to look at the whole list at once. We set up two markers, or pointers. We'll put a left pointer at the very beginning of the list and a right pointer at the very end. This whole area between them, that's our search space. So what's the first move? We don't check the start. We don't check the end. We jump straight to the middle. We find the exact center point of our current search space. Okay, we've landed on the middle value. Now we just ask one simple question. Is our target bigger or smaller than this middle number? Let's say our target is 11, and the middle value is 7. Since we know, and this is crucial, that the list is sorted, that one little comparison tells us so much. So just think about it for a second. If our target, 11, is bigger than the middle number, 7, and the whole list is in order, where could it possibly be? There's no way it's in the left half, right? It has to be somewhere over in the right half. And right there, that's the magic trick. With one single check, we just gotta throw away half of the entire list. We can completely ignore everything on the left. All we do is slide our left pointer up to where the middle was, and boom, our problem is now half the size it was a second ago. So what now? Easy. We just do the exact same thing again, but on this new, smaller chunk of the list that's left over. You guessed it, we find the middle of our new, shrunken down search space, right between our new left pointer and our right pointer. And bingo! This time, the new middle value is exactly our target. We found it. In a list of 8 items, that took us, 2 checks? But look, the really important thing here isn't that it was a little bit faster. It's about how this scales up. That's where things get really wild. Okay, let's talk about the power of logarithms. This idea is why binary search is such a huge deal in computer science. This superpower has a technical name, logarithmic time complexity, or O of log n. Now don't let the fancy terms scare you off. All it really means is that even if your list gets ridiculously, massively bigger, the number of steps it takes to find something barely goes up at all. Every single guess cuts the problem in half, which is just an insanely efficient way to work. And this is where it just gets absolutely mind-blowing. Let's say you have a sorted list with 10 million items in it. How many checks do you think it would take binary search, worst case scenario, to find any single item? The answer is about 24. I'm not kidding. Just 24 checks to find one item out of 10 million. Let's just look at that comparison. Our slow and steady linear search might have to make up to 10 million checks. Binary search, about 24. This isn't just about being faster. They're not even in the same sport. This is the kind of difference that takes a process from taking, say, a few weeks to run, down to taking less than a second.
All right, so what does this actually look like in code? How do we translate this logic into a set of steps a computer can follow? It's actually a lot simpler than you might think.
So here's the recipe. First, you set up your left and right pointers at the start and end of the list. Then you kick off a loop that keeps running as long as your search space is valid, as long as left hasn't passed right. Inside the loop, you always calculate the new middle. If that middle element is your target, awesome, you're done. You can return its location. If your target is smaller, you know it has to be on the left, so you pull your right pointer in. If it's larger, it has to be on the right, so you push your left pointer up. You just repeat that loop, slicing your search area in half every time until you either find the target or the pointers cross, which just means the item wasn't in the list to begin with.
Okay, so this algorithm is a beast on a perfectly sorted list. But what happens when we get a little curveball? Let's talk about the final twist, the shifted array challenge. Check this out. What if you have an array that is sorted, but it's been rotated? Like someone took a chunk from the end and slapped it onto the beginning. The numbers are still in a sorted sequence, just broken in the middle. The problem now is that when you jump to the middle, you can't be sure which half is which. Our simple rule of is it bigger or smaller doesn't reliably tell you where to look anymore. The basic algorithm breaks.
This is a classic problem you'll see, and it's designed to test if you really get the core idea of dividing the problem. So how would you adapt binary search to handle this? The simple version is broken, but the underlying principle can still work. I'll give you a hint. It involves figuring out which side of the middle point is still perfectly sorted. Thinking through how you'd solve that is your takeaway challenge for today.